Hello everyone, I am Savita Kuntoji, studying in BSc second semester VCM combination. In this video, I am going to discuss about my chemistry assignment topic. My topic is alkyl halides and relative reactivities of halogen in alkyl halides. And also I will discuss about allyl halides, vinyl halides, aryl halides and alkyl halides. In this video, I will cover the following topics. First, introduction to alkyl halides, then definition and classification. Next, relative reactivity of halogens. After that, types of halides like allyl, vinyl, aryl and alkyl halides. Finally, conclusion and reference. Now, let us start with introduction. Alkyl halides and their classification are very important in organic chemistry. We also study the relative reactivity of halogens in these compounds. Alkyl halides and related compounds such as allyl, vinyl, aryl and alkyl halides show different reactivities in nucleophilic substitution reactions. This variation due to differences in structure, bond strength and stability of intermediates. Let us see the definition of alkyl halides. Alkyl halides are organic compounds in which one or more hydrogen atoms are replaced by halogen atom, such that the halogen is attached to sp3 hybridized carbon atom. For example, methyl chloride. Classification of alkyl halides. First one is monohaloalkanes. The alkane contain only one halogen atom. For example, methyl bromide. Let us see the classification of monohaloalkanes. Monohaloalkanes are classified into three types. First one is primary haloalkanes. The halogen attached to carbon bonded to one alkyl group. For example, ethyl fluoride. Second one is secondary haloalkanes. The halogen attached to carbon bonded to two alkyl groups. For example, isochloropropane. Third one is tertiary haloalkanes. The halogen attached to carbon bonded to three alkyl groups. For example, tertiary butyl chloride. Alkyl halides second classification is dihaloalkanes. Dihaloalkanes means the alkane contains two halogen atoms. Dihaloalkanes again classified into two types. First one is geminal dihalides. Geminal dihalides means the two halogen atoms are attached to the same carbon atom. Second one is vicinal dihalides. The two halogen atoms are attached to two adjacent carbon atoms. Next, alkyl halides third classification is polyhaloalkanes. The alkane contain more than two halogen atoms. Now we discuss relative reactivities of halogen in alkyl halides. Effect of nature of halogen. For the same alkyl group, the reactivity depends on the halogen atom, because reactivity depends on bond dissociation energy of carbon halogen bond. Reactivity is inversely proportional to bond strength and size of halogen atom. Example, iodine is largest, so longer and weaker bond. Fluorine is smallest, so shorter and stronger bond. Next, effect of alkyl group. When halogen is same, reactivity depends on type of carbon. Reasons: stability of carbocation intermediate, more alkyl group plus I effect. This stabilizes the carbocation. Higher the number of alkyl groups attached to the carbon atom containing halogen, greater the reactivity. Among primary alkyl halides with same halogen atom, when halogen atom is same, the reactivity of primary alkyl halides depends on the nature or size of the alkyl groups. Reasons: plus I effect. As chain length increases, plus I effect increases. This makes the carbon halogen bond stronger. Bond strength. Reactivity decreases with increase in alkyl group size. Stronger carbon halogen bond, harder to break. Steric hindrance. More steric hindrance, less reactivity. Let us see relative reactivity of halogen atom in allyl halides. Allyl halides are more reactive than vinyl halides because when halogen leaves, an allylic carbocation is formed. This carbocation is stabilized by resonance. The positive charge is delocalized, increasing stability. More stable intermediate, higher reactivity. Conjugation with double bond. It involves overlap of p orbitals, leading to delocalization of electrons. This stabilizes the carbocation and transition state. Next, Relative reactivity of halogen atom in vinyl halides. Vinyl halides are least reactive halides because strong carbon halogen bond. Due to interaction with adjacent double bond becomes strong and rigid. sp2 hybridized carbon. Halogen is attached to double bonded carbon. Bond is shorter and stronger. Next, relative reactivity of halogen in aryl halides. Aryl halides are less reactive compared to alkyl halides because resonance strengthens carbon halogen bond. Lone pair of halogen enters benzene ring. Carbon halogen bond gets partial double bond character. Bond becomes strong. sp2 hybridized carbon. Carbon attached to halogen sp2 holds halogen tightly. Unstable phenyl carbocation. No proposed stabilization. SN1 not possible. SN2 is difficult. Benzene ring blocks attack. Steric hindrance. Now we discuss relative reactivity of halogen in alkyl halides. Alkyl halides are more reactive compared to aryl halides because resonance stabilization of carbocation. When halogen leaves benzyl, carbocation is formed. This benzyl carbocation is highly stabilized by resonance, delocalization over multiple positions. Very stable, reaction becomes fast. Stabilization of transition state. Benzene ring helps stabilize the transition state. Lower activation energy, faster SN2 reaction. No strong carbon halogen bond. In alkyl halides, halogen is on sp3 carbon. Normal carbon halogen bond, easier to break. Last one, conclusion. Final reactivity order is aryl halides are greater than vinyl halides, alkyl halides are greater than aryl halides, allyl halides are greater than alkyl halides, or alkyl halides are greater than allyl halides. Reference BSc second semester textbook. Thank you.